We are sold autonomous agents as the next step in software evolution, systems designed to grow with you. But for practitioners, this growth is often an architectural trap. When we move from simple prompts to complex agents like Hermes, we hit a hard ceiling where coordination overhead kills performance and memory isolation fails at scale. The paradox isn't that AI gets smarter, it's that the systems designed to them become brittle faster than they get useful. This video breaks down why growing with you is actually an engineering liability without specific architectural trade-offs in place. The transition from single-prompt large language models to autonomous agents introduces three distinct failure modes identified by recent research and community data. The first major hurdle involves the relationship between coordination overhead and capability. Research testing 180 configurations across 4 benchmarks, including finance and web navigation, reveals that multi-agent systems do not automatically scale performance as we expect. In fact, once a single agent exceeds roughly 45% capability on sequential logic tasks, adding more agents degrades performance by up to 70%. Independent agents amplify errors by a factor of 17.2 times compared to centralized control, because unchecked propagation creates cascading failures that are difficult to trace or fix in production. This means that if your task requires strict sequential logic where one step depends on the previous outcome being perfect, adding more intelligence does not help. It actively hurts. You end up with a swarm of agents arguing over minor details while the core workflow stalls. The data shows that for many common engineering tasks, a single robust agent often outperforms a complex swarm by 30 to 70% simply because there is less noise and no coordination friction to manage. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The second failure mode we face is what researchers call the dark matter bottleneck. Current cloud-centric designs fail agentic tasks that require high-fidelity local context, such as detailed file hierarchies or live sensor streams from your development environment. As noted in edge computing research, this transient data acts like dark matter for AI agents. It degrades rapidly when transmitted to a remote server over the internet. Scaling laws based on model size are insufficient here because an agent needs structural coupling with its immediate environment rather than just larger models that live far away. When you send local context up to the cloud and back, the latency increases, and crucial details get lost in transit or sanitized by security filters before they ever reach the intelligence layer. This creates a scenario where your AI appears less capable, not because it is dumb, but because its view of the world has been artificially narrowed during transmission. The future of agents isn't just about bigger models. It is about moving processing closer to the user on the edge to preserve local context that gets lost in transit. Without this proximity, you are building intelligence on a foundation of incomplete information, which leads to hallucinations and incorrect actions when deployed in real-world scenarios where every byte matters. The third critical issue we must confront comes from the multi-tenant reality found in open-source frameworks like Noose Research's Hermes agent. A specific architectural flaw prevents scaling beyond single-user deployments, creating what engineers call a one-agent equals one-tenant limitation. Memory operations currently bypass isolation hooks, causing sensitive data to leak between sessions where private context mixes with public contexts or other user inputs. This is not a theoretical risk. It is a documented issue in the project's tracking system that forces developers to run separate processes for every single user context to ensure safety. This operational model creates an inefficient and unsustainable path forward because you cannot simply spin up more instances without creating massive overhead costs. If you try to scale this architecture horizontally, you must fork entire processes for each interaction rather than sharing a safe runtime environment. This means that as your user base grows, your infrastructure requirements grow exponentially instead of linearly. The cost of maintaining isolation becomes the primary bottleneck, not the intelligence itself. For the software engineer or AI practitioner, these findings reframe how we approach system design entirely. You cannot simply swap a prompt-based workflow for an autonomous agent architecture expecting linear gains in productivity because complexity is never free. It introduces exponential risks of error propagation and data leakage unless explicitly architected to contain them from day one. The practical takeaway requires a shift in judgment regarding when you deploy these systems and how you structure your infrastructure around them. You must not scale agents blindly based on hype or demo videos. If your task requires sequential logic, stick with single robust architectures where error rates remain low. Only use multi-agent systems for parallelizable tasks like financial analysis, where centralized coordination can boost performance by roughly 81% without introducing cascading failures. Furthermore, you need to design for isolation first before adding any intelligence features. Without a runtime that supports tenant isolation, scaling to multiple users is impossible without data leaks or running inefficiently on separate processes, which drains your budget and slows development cycles significantly. The engineering judgment required here moves beyond asking if the AI can do the task. We must ask if our architecture is built to contain the complexity of an autonomous agent. We are moving into a phase where software stability depends less on model size and more on how well we manage the interaction between local context, memory isolation, and coordination overhead. The tools that work today may break tomorrow not because they stopped learning, but because we tried to stretch them beyond their architectural limits without paying attention to the underlying constraints of distributed systems. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.